Hi guys, welcome back to engineeringtalks.com. The previous video was about the shear force and bending moment diagrams of a simply supported beam with an eccentric point load. In this video, we'll discuss the shear force and bending moment diagrams of a simply supported beam with a uniformly distributed load over it. So, happy learning, and if you haven't subscribed the channel yet, please do subscribe and press the bell icon. Here I have shown a simply supported beam with a uniformly distributed load over it. A uniformly distributed load is the one which is spread over a beam in such a manner that the rate of loading is uniform throughout the length of the beam over which this UDL acts. Here the rate of loading is given by W per unit length and the length of the beam is L. Due to this UDL acting over this beam, we will have reactions at both the supports of the simply supported beam. Let RA be the reaction due to hinge support at the end A and let RB be the reaction due to roller support at the end B. I already told you that for solving the numerical problems, we have to convert this UDL into a point load whose value will be equal to the product of the rate of loading into the length of the UDL. Here, in this case, since the UDL is spread over the entire length of the beam, we can say that this point load will be equal to the rate of loading into the length of the beam. And this point load will be acting at the center of the UDL. In this case, it will be acting at the center of the beam itself. So, this WL, that is this point load, will be acting at a distance of L by 2 from both the ends of the beam. Now, due to this point load WL acting at the center of the beam, we'll have reactions RA equal to RB equal to WL by 2 in order to resist or support this externally applied point load. Let's find out the shear force and bending moment values acting along the length of this beam. We know that RA equal to RB equal to WL by 2. Now, in order to find out these shear force and bending moment values, we have to consider a section on the beam. Let this section be at a distance of x meters from the end A. And let Fx be the shear force and Mx be the bending moment at this section. Now, the shear force at this section will be equal to the algebraic sum of the forces acting on either the left portion or the right portion of the section. Let's consider the left portion of this section. This is the left portion of the section. On this left portion, we have a reaction force RA acting in the upward direction and a UDL acting over a length of x meters. We know that for solving the numerical problems, we have to convert the UDL into a point load whose value will be equal to the product of the rate of loading and the distance over which the UDL acts. So this point load will be equal to W into X and it will be acting at the center of the UDL. So here the center of the UDL means at a distance of X by 2 from both the ends. So we have a reaction force RA acting in the upward direction and a point load Wx acting in the downward direction. And we know that on the left portion of the section, a force acting in the upward direction will be considered as positive and any force acting in the downward direction will be considered as negative. So RA is acting in the upward direction, so it is positive, and Wx is acting in the downward direction, so it is negative. Therefore, the resultant of these two forces will be equal to RA minus Wx and it will be equal to the shear force at this section. Therefore, Fx is equal to plus RA minus Wx, which is equal to WL by 2 minus Wx. RA is WL by 2. So, just substitute WL by 2 in the place of RA. So, WL by 2 minus Wx. Now, we can vary this distance x along the length of the beam and find out the values of shear force along the entire length. Now, at this end A, x will be equal to 0, right? Therefore, Fa will be equal to W by 2 minus 0. So, W by 2. So, at the end A, shear force is equal to WL by 2. Now, at the end B, we will have x equal to L. Therefore, FB will be equal to WL by 2 minus WL in the place of x. Just substitute L. Therefore, WL by 2 minus WL, which will be equal to minus WL by 2. Therefore, at the end B, shear force is equal to minus WL by 2. Now at this point C, we'll have FC equal to WL by 2 minus WX. In the place of X, just substitute L by 2. Therefore, WL by 2 minus WL by 2, which is equal to 0. Therefore, the shear force is 0 at this point, that is at the center of the beam. From this equation, that is Fx equal to plus Ra minus Wx, which is equal to WL by 2 minus Wx, it is clear that shear force is proportional to the distance of this section from the end A, which means that shear force varies according to straight line law. It is a function of the distance x from the end A. Let's now find out the bending moment at this section. For that, we have to consider either the left portion or the right portion of the section. Let's consider the left portion of the section. Here we have a reaction force Ra acting in the upward direction and a point load Wx acting in the downward direction. Now the bending moment at this section will be equal to the resultant of the bending moment caused due to these two forces. So this reaction force has a tendency to rotate the beam in the clockwise direction like this. In the clockwise direction with respect to this section, and any moment in the clockwise direction on the left portion of the section will be considered as positive. Therefore, the bending moment at this section due to this reaction force Ra will be equal to Ra into perpendicular distance. Perpendicular distance is x. So, Ra into x will be the moment at this section due to the reaction force Ra, and it will be positive. Now, this point load Wx has the tendency to rotate the beam in the anti-clockwise direction like this with respect to this section, and any moment in the anti-clockwise direction on the left portion of the section is considered as negative. Therefore, the bending moment at this section due to the point load Wx will be negative, and it will be equal to Wx into perpendicular distance, and the perpendicular distance is x by 2. So, Wx into x by 2 will be the moment at this section due to the point load Wx, and it will be negative. Therefore, the resultant bending moment will be equal to Ra into x minus Wx into x by 2. So, it will be equal to WL by 2 into x minus Wx square by 2. Now, at this end A, x will be equal to 0. So, bending moment at this end will be equal to Ma, which is equal to WL by 2 into 0. Just substitute 0 in the place of x, minus W by 2 into 0, which is equal to 0. So, at the end A, bending moment is 0. Now, at this end B, x equal to L. So, bending moment MB will be equal to W L by 2 into L, that is WL square by 2 minus W by 2 into L square, that is WL square by 2, which is equal to 0. So, at the end B, bending moment is equal to 0. We already know that at both the ends of a simply supported beam, we have bending moment equal to 0. Now, at this point C, x equal to L by 2. So, MC will be equal to WL by 2 into L by 2 minus W by 2 into L by 2 the whole square, that is L square by 4, which will be equal to WL square by 4 minus WL square by 8. So, it will be equal to WL square by 8. So, the bending moment at this point, that is at the midpoint of the beam, will be equal to WL square by 8. And from this equation, that is Mx equal to WL by 2x minus Wx square by 2, it is clear that the bending moment is proportional to the square of the distance of the section from the end A. So, the bending moment varies according to parabolic law. Let's draw the shear force diagram. For that, we have to draw the baseline first. This is the baseline. Now, at this end A, we have shear force is equal to plus WL by 2. So, we'll mark that above the baseline. Now, at this end B, we have shear force is equal to minus WL by 2. So, we'll mark it below the baseline like this. Now, this is plus WL by 2 and this is minus WL by 2. Now, we'll join this point and this point using a straight line like this. So, here we have at the center of the beam, we have shear force is equal to 0. And this is the shear force diagram for a simply supported beam with a uniformly distributed load over it. And we can shade these two regions and mark it as positive and negative. Let's draw the bending moment diagram. For that, we have to draw the baseline first. We know that the bending moment at both the supports of a simply supported beam is 0. That is MA equal to MB equal to 0. Now at the point C, we have the bending moment equal to WL square by 8. And the bending moment varies according to parabolic law. So we can draw the bending moment like this. Like this. The bending moment is 0 at both the ends and it is equal to WL square by 8 at this point. And you can now shade this region and mark it as positive. And here the bending moment is maximum at a point where the shear force is 0 or where the shear force changes its sign. These are the shear force and bending moment diagrams of a simply supported beam with a uniformly distributed load over it. From these two diagrams, it is clear that the bending moment is maximum at a point where the shear force is 0. So we can conclude that the bending moment will be maximum at the point where the shear force changes its sign or shear force becomes 0 when it changes its sign from positive to negative or vice versa. Please do like and share the video and subscribe the channel. Thank you.